All right, so this video is going to help you get through the calculations we need to do with the heating curve. And to do this, we're going to be using the following problem. The heating curve shown below is for ethanol. How much heat is required to warm a 50-gram sample of ethanol at negative 130 degrees Celsius to 88 degrees Celsius? Also at the bottom here, they've given us the heat of fusion, which we'll need, the heat of vaporization, and they've given us the three specific heat of a solid, a liquid, and a gas form of ethanol. So before we jump into doing the calculations, let's break down the graph that they've given us. So I've labeled this part of the graph A. What is happening at this part of the graph is we have solid ethanol. And you notice that the temperature is going up. So in this case, we are doing an endothermic reaction. So we are adding heat to the ethanol. So to do the calculations of how much heat, we need to use the Q equals mc delta T. And remember, M is the mass of the sample, C is the specific heat. In this case, it's C sub S, meaning we need the solid specific heat. And delta T is going to be what is the change in temperature? What are we starting at and where are we going? So again, the needed information is we need that specific heat of the solid, or C sub S, and they give it to us next, okay? The next part of the graph, which I've labeled B, is where we are going from a solid to a liquid, okay? So that means all the heat energy that we are putting in is going to break down intermolecular bonds and things that are keeping them together as a solid, and it's breaking those bonds to make it more of a liquid, or more so the molecules can move around. To do that calculation, Q equals M heat of fusion, or delta H fuse. Okay, and they give us that information as well, and we'll use that when we go into it. Notice there is not a change in temperature, because if you look at the graph is not changing temperature. It is setting at a constant temperature while it is doing the conversion from solid to liquid. Now, oh, wrong way. Now the part of the graph I labeled C, again, is now everything is a liquid, or our sample's all liquid, and we're heating that liquid. So we go back to the same equation we somewhat used in A, Q equals mc delta T, but instead of the specific heat of a solid, we now have to use the specific heat of a liquid. And they give that to us again as our needed information. Depending, sometimes we can stop in the middle, but in this case, for our equation, we're going to keep going. So then if I go to the next part, which is what I've labeled letter D, what is happening at letter D is we have a liquid now that is starting to become a gas. So this is when our substance is going to start boiling, that we see normally with water, and we would see the same thing with ethanol when we got to that 78 degrees Celsius. Again, notice there's no temperature change, so our equation we would use is Q equals M heat of vaporization, because here we're having that vaporization process happening. And again, they need to give us that heat of vaporization, and they do. And then the last part of the graph is letter E, and at letter E, our whole sample is now gas, and we've contained it, and we're just heating that gas and able to figure out how much heat is going in to make that gas hotter and hotter. So again, we go back to that Q equals mc delta T, but in this case, we need the specific heat of the gas form of ethanol, not the liquid or the solid, and that's what we're going to use. So let's jump in. I'm basically going to do this section by section. So let's go back and look at the problem given to us. So we see that we're starting out at a negative 130 degrees Celsius. So if we think about it, that's going to be roughly down here on the graph. And where are we wanting to go? They're having us go to 88 degrees Celsius, which is going to be somewhere up here on the graph. Okay, so basically we have to do a calculation for section A, section B, section C, section E or D, and also section E. So I'm going to do this step by step. So let's jump into section A. So if we go back to section A where we were, we have a solid that we were just heating. And we're going to have to use that Q equals mc sub S delta T. So we need that specific heat for the solid, which again, we have in the table that we made or I showed you. So we plug in, our mass is 50 degrees or 50 grams. Our C delta or C sub S, or specific heat of a solid, is 0.97. And then to get our change in temperature, we have to do final temperature minus the initial temperature. Well, if we think about it, our initial temperature is at negative 130 degrees Celsius. Our final temperature, because we can only go up to this part of the graph as a solid, has to stop at that melting point. In this case, the melting point of ethanol is a negative 115 degrees Celsius. So our final temperature through this part of the graph is going to be negative 115 degrees Celsius. So we're doing a change in temperature of 15 degrees Celsius. So then we plug all those numbers into our equation. So we have 50 times 0.97 times 15, and we get that that's 727.5 joules. But following sig figs, we'd have to round it to 2 sig figs, so it'd be 730 joules. Okay, and we're going to go put this in this table for right now because we're going to have to add them all up at the end. But we found out letter A, or section A. We're going to put it in the table. Now let's go look at section B. So for section B, again, we have it going from a solid to a liquid. We don't have to worry about the temperature because the temperature is constant when that's happening. So we just need this M and then the heat of fusion. So again, our mass is 50.0 grams of ethanol. Our heat of fusion is 105 joules per gram. So we plug those into the equation, and we do 50 times 105, and we get that it's 5,250 joules. And that works out perfectly because both of our values had 3 sig figs, and that number has 3 sig figs. So let's go put that in here for part B. And again, we're going to need it later at the end to add these all up to figure out the total number of joules that were needed to complete this transformation. So let's go look at part C. So again, at part C, we are heating a liquid. So we're going to have a change in temperature. And since we're going all the way from it being a very cold liquid at negative 115 degrees Celsius to, because we're going from here all the way up to here to it being 78 degrees, that's going to be our change in temperature. So again, our mass is still 50 grams. Now, in this case, we need the specific heat of the liquid because we're in liquid phase, and that's going to be the 2.43 joules per gram degree Celsius. And then again, we have to find that change in temperature. So our final temperature, we're heating it all the way up to 78 degrees Celsius, and our initial temperature is at negative 115 or 115 degrees Celsius, because that's where we have converted it all to liquid, and we're right here at this little bend getting ready to start heating the liquid. So again, we plug in those 3 numbers into our equation, multiply it out, and we get 23,449.5 joules. But of course, we need to follow sig figs. We need to round it to 3 sig figs, which would be 23,400 joules. And we're going to go put that in our table for letter C. All right, so let's go figure out letter D. So for letter D, again, we're setting at the constant temperature, and we're just now converting it from a liquid to a gas. So we need the heat of vaporization to do that and the mass. So again, mass is still 50 grams. We have a delta H vape, which is our heat of vaporization of 854 joules per gram. Plug those into our equation and multiply, and we get 42,700 joules. And again, it matches up perfectly for our sig figs of 3, so we can just take that and put that in section D. So we have one last part to do. We need letter E. Now, letter E is a little different because, again, we need the specific heat for the gas, but we're still using Q equals MC delta T. Again, we still have 50 grams. And we need this new specific heat of a gas, 1.70 joules per grams degree Celsius. But here's where it gets a little different. We know our initial temperature is going to be right here at the 78 degrees. But we're not going all the way to the top or to a final temperature. We are going to 88 degrees. So we know that's roughly up here. So our final temperature is going to be 88 degrees, and we're heating it from a hot liquid at 78 degrees Celsius. So that's where we're going. So plug in the numbers, multiply them out, and we get 850 joules. And actually, that's perfect. All we need to do is put a little, it only has 2 sig figs because of our subtraction right here when we plugged it in. Okay, so we'll go put that in our table, 850 joules. Now we have it all the way from negative 130 degrees all the way up to 88 degrees Celsius. So all we have to do is take all those Q values, so Q total, or the total amount of heat, is going to be the heat required to go in part A, B, C, D, and E. So we have to add all 5 of those up, add them all up, and we get 72,930 joules. But again, following our sig fig rules for adding, the lowest place value they all have in common is the hundredths place value. So we'd have to round it to 72,900 joules. Okay. I hope you have found this very informational. I hope this will help you as you go through the heating curve of water lab, and have a good day.